Hi everyone, and welcome back to another episode on Metasploit Encoders. In this part, we'll talk about the optimized SUB encoder, which I've chosen for a few reasons. First, it's actually a really interesting encoder because it only uses push, pop, and subtract instructions. Neat! And second, because it requires some manual tweaks and debugging steps in order to get it up and running correctly. So it's slightly more involved than the previous ones we've seen so far. First, let's generate a corresponding executable that uses the encoder. Then, after that, generate the C array of bytes that we will incorporate in our wrapper code. One thing you'll notice straight away is that its size will be pretty large. In this case, 1117 bytes, more than 1 kilobyte. I've actually run the same command. Let me copy the correct one. Okay, we have the executable and we will also have the shellcode as an array of bytes. Interestingly, if we try to execute the binary generated by MSFVenom, it crashes. We have to figure out what's happening. Hang in there because it's going to be interesting. First step. We have here the array generated by MSFVenom. We'll add that to a wrapper code exactly as we've done in the past videos. Let's see. Unfortunately, the wrapper crashes as well, kind of expected. We will use IDA Pro to debug the code and find out what's happening. I will use the cross-reference trick to quickly reach the main function. In the main function, set up a breakpoint on the place where the shellcode is executed. Then run the file in the debugger. As I was saying before, this encoder generates only push, pop, and sub instructions. That's actually really clever. The entire first stage of this encoder follows this pattern. Let's understand it. An instruction is generated using subs and then pushed on the stack. So each double word of the shellcode, the simple message box shellcode, is created using only subs instructions. Very clever indeed. Let's go step by step through the shellcode. Notice that it crashes at this point over here. This is something that we'll need to fix, but this crash doesn't happen all the time. I want to show you something else. I'll set a breakpoint at the end of the decoder. Set the breakpoint here and let the execution continue. It crashes again. Let me try another time. Okay, another attempt. Press F7. Still crashes. We will see in a minute the reason why. Let's talk about something else first. Because it's random, we can sometimes go past the crash and set a breakpoint at the end. And let it run. I will execute the last instruction of the decoder part. Let's also enable the display of OP bytes. The last assembly instruction code is 50, this one here. Check with the shellcode bytes. Of course it will crash, because all the bytes here are 0, there's nothing to execute. This works by pushing double words into the stack. If we look here, the stack pointer starts with 95FC. But the instruction pointer is in a totally different address block. Let's go manually to RSP and see what's there. If we convert that to code, we have our message box shellcode, exactly what we've seen before. The first hurdle we have to overcome is that we need to specify a base register. Other MSF shellcodes, like the Alpha Mixed Encoder, also use a base register. The base register refers to a register that points to our shellcode, and we will be able to use it afterwards to reach our code. Let's see that this makes a big difference. Copy the newly generated shellcode and embed it into our application. Next, we'll also need a bit of inline assembly. We've used EBX as the base register, so we'll move the address of the shellcode into EBX. Let's see how the new code looks now in IDA Pro. Okay. Go to the shellcode and set a breakpoint before its execution. Then take the breakpoint. Have a look at the registers. In this case, RBX starts with E1, RAX starts with E1. And very important, notice here that the RSP register points very closely. Just check the difference between RSP, which is the stack pointer, and RBX, which is the base for our shellcode. The difference seems like the size of the shellcode, which we know it's around 1000 and something bytes. This is important, keep this in mind. Remember, the size was 1117 bytes, which converted to hex gives us 45D. The logic of the encoder has calculated an offset where it will start to decode the next stage of the payload. That's why it didn't work the first time. After this offset, the payload will be decoded on the stack. We can advance a few instructions and then, as before, set a breakpoint after the last push instruction. Very important, notice that at this point the RSP register, which is for the base of our shellcode, and RIP, the instruction pointer, are very close. To make this clearer, let's convert this to code. Let's see, so RSP ends in 461. We actually need to convert from RSP. Let's see, 461. After we do another push, we get our actual expected instructions that we've seen before. Starting with FLDPI, FSTENV, and so on. This is the message box shellcode. If we step over by pressing F8, we'll have a crash again. We'll reach a point where we cannot continue the execution. The problem is not yet very obvious here. After we executed the FSTENV instruction, some bytes over here were changed, they were overwritten. Let's run it again. And understand what's happening. Set a breakpoint here. This instruction will overwrite 28 bytes at the address ESP-C, and in this case ESP points somewhere around here. Basically, this instruction will overwrite the beginning of the shellcode itself. How to overcome this? Simple. We'll leave some space before the shellcode. Meaning between the shellcode and the decoder decryptor. Let's do this manually. For example, by adding another, let's say 32 hex bytes to EBX. And we'll fill those bytes with a nope sled. We can do that easily using the memset function. Actually, I'll do this before copying the shellcode. So, we will memset the address /x90, which is a nope instruction, a very well-known one, and finally the size of the memory block. And to make things more clear, I'll copy only the number of bytes needed. Meanwhile, the length of the shellcode 1117. We don't need to copy more than that. Let's compile it again and see the difference. We still have a crash, so we need to continue the investigation. Okay, this is becoming interesting. Go back to the main function, using cross-references as before, and set the breakpoint. Set the breakpoint over here. Notice we got rid of the crash we had in the first version after we set the base register. At the end of the shellcode, see that everything here is actually nopes. Press F9. We have a large nope sled here until we reach this point. And here's the FSTENV instruction again. This will extract the FPU operating environment at the memory location specified in the destination operand. In this case, ESP-C. Let's see. It should be somewhere around here. Press F8 and check. We have a similar problem as before. These are the bytes added by FSTENV instruction. And the beginning of our shellcode has been overwritten again. Let's debug it one more time to clarify what's happening. Let me restart it. I pressed F9 too quickly. F7. At this point, let's check the values of the registers. In this case, RSP ends in 48F. This instruction will overwrite bytes at an address that overlaps with the beginning of our shellcode. Even if we have this large NOP sled, the RSP is too close to the beginning of our shellcode. Notice the beginning is 491 and RSP is 48F. What's the difference? Too close. We actually need 24 bytes for the output of this instruction. The solution to this problem is actually documented if we look closer. A workaround is documented in the source code of the encoder itself. It's a very interesting trick. Let's find it. This is for another episode. It has quite a lengthy description. Due to the fact that many payloads use the FSTENV approach, exactly as our message box payload, to get the current location in memory, there is an option to protect the start of the payload by setting the override protect flag. Browse through this code. Notice that override protect is a flag that can be set to true or false. What's happening when this flag is set? The shellcode will add some instructions after the decoder to bump the stack by 0x20 bytes. I couldn't find a way to get this option to work automatically by setting this flag, but that's no problem. We can set it manually in our shellcode. Very important, we need to set this at the end of the decoder, so actually around here. At this point, imagine what happened when we did the debugging. At this point, we have the next stage already decoded on the stack. Let's compile it again and see. And have a look in IDA Pro. Go back to the main function and set the breakpoint. I actually forgot something very important. After adding the extra instructions, we also have to modify the size, because we want to copy these 3 bytes as well. So the final size would be 1117 plus 3, 1120 bytes. Recompile. OK. Let's see the difference in this case. Set the breakpoint on the call to the shellcode and start the application. Step through a few instructions, then set up a breakpoint right at the end of the first stage decoder. Let's say around over here should be fine. Then another breakpoint here. So notice the value of RSP at this point. RSP ends in 46F and RIP in 48F. So there is a larger gap between them. This was caused by the last sub instruction that we added manually. Just to convince ourselves, these are the bytes. 83EC20. Check here. 83EC20. Basically, we're bumping the stack by 0x20. We can see the bytes put on the stack by our code. If we continue, sure enough, we'll have our message box. Great, exactly as we wanted. We can now run the executable without the debugger and we'll get the same message box. I know this was a lengthy video, but I believe we've seen some important lessons and tricks here. First, we need to be aware that some Metasploit shellcodes need manual adjustments in order to function. For this one over here, we've done some things manually, like setting the base register, applied the override protect flag manually, and finally set the base register with the address of the shellcode. We also had to create some space between the decoder and the next stage payload. After all these steps, we've been finally able to get the shellcode to run and obtain the message box. Thank you very much for watching, and I hope I'll see you in the next episodes. Also, feel free to suggest other interesting topics that you would like to deep dive into in the next videos. Cheers!